So Tony, thank you very much again for stepping up, and we'll look forward to hearing your presentation for me again for the people on this webinar for the first time. So take it away.
Gerald, thank you very much. And I guess being here up in Canada, we're hockey enthusiasts in general, and we always say that in the game of hockey, you can't play the game the same way, and you have to adjust. And sometimes circumstances force the adjustment. And certainly, Gerald, I'm pleased to help with the adjustment here. What I want to do today is I want to share with you not only a case study related to the reuse of existing steel pile foundations, but kind of slant the presentation towards the significance and the importance of making smart investment decisions, and specifically, investing in testing, right? But before I do that, as you see my presentation outline, the very first bullet, I just wanted to kind of get the Ministry of Transportation of Ontario here in the province of Ontario on the radar for you folks. So if you could bear with me just for a couple of minutes, I'd like to talk a little bit about our infrastructure and our commitment to sustaining our infrastructure. Then I'll get into the details of the case study, which is a project in one of our 5 regions, West region specifically. And there's a number of things that I want to share with you as indicated in this presentation outline here. And then I'll obviously make some conclusions and share those conclusions with us all. So with regards to our infrastructure, as you could see here on the right-hand side, in our inventory, we've got about 3,000 bridges. We got about 17,000 kilometers of highways, about 5,000 structural culverts, about 50,000 non-structural culverts. Our total asset value is about 100 billion. And we take a lot of pride in moving Ontarians safely, reliably, and efficiently. And in doing so, of course, trying to encourage economic prosperity. That's why when you look at that last bullet, we move about $3 billion of goods and services daily on our infrastructure. So a big part of our mandate, and certainly one of our priorities, as indicated here on this slide, is to sustain our infrastructure through smart investment decisions and innovation. And testing and investing in research type of project is something that we take a lot of pride in. So one of those areas that that we feel is certainly beneficial to pursue moving forward, and we've started and we got some momentum with this, right? And that is to look at the reuse of existing foundations. So with the infrastructure, as I just described, and particularly our infrastructure aging, we need to look at new ways of doing things so that we could be more cost effective and be more responsible to our taxpayers in our province. So, one of the things that we are doing is we're looking more and more into reuse of existing foundations, as opposed to just building new foundations and new structures entirely. And obviously with that, there's a lot of benefits. I mentioned cost, but there's minimization of traffic disruption, there's schedule, there's environmental benefits as well. So there's a process, and we've got a draft guideline that we have used and will continue to upgrade, because we take a lot of pride in our technical leadership. But the process, as you can see here, I won't go into all the bullets here or all the numbers here, but it starts with a preliminary assessment. Then you go through a risk analysis, an LCCA, life cycle cost assessment, and then go through the detailed assessment, which is looking at the capacity, looking at the extended service life, the durability, and the integrity of the particular foundation system. So at this particular site, the Greenock River Bridge, it's An existing bridge, you could see here by the photo that the superstructure is not in the best of condition. It was built in 1971. It's a single span structure, about 18 meters long, with approach embankments as indicated here, about 3 to 4 meters high. The existing abutments are founded on driven steel edge piles, 11 at each abutment for a total of 22, about 8 meters long. The piles are battered, and that's important, as I will describe later to note. And the piles were originally designed to carry a particular load, of course. In this particular case, 70 tons, or in metric 630 kilonewtons per pile. And here's a plan showing the actual foundation layout, illustrating the 11 piles at either abutment. And the next slide just shows an elevation of the piles. The piles are, 310 by 79 piles. Our go-to foundation system in this neck of the woods, because of the availability and the conditions that we have here. Subsurface conditions are usually 310 by 110, but notwithstanding, what we did in our preliminary assessment so that we could determine if in fact the reuse of existing foundation option was the preferred option, as we went through a comparison of reuse versus replacement, and our comparison came back that the preferred option unequivocally was to proceed with replacement of the superstructure deck and the superstructure girder, and keep the foundations. And the reasons are indicated on the slide, primarily the traffic mobility, but as I said before, economic sustainability and environmental advantages as well. So then we proceeded into the detailed assessment of the existing piles, and this is where now the investment in testing comes into the picture. So at this particular site, as you can see by the slide on the right there, a close-up there, the preferred method to investigate existing piles is what we call a direct approach, where you try to expose the piles if you can, if the conditions, both site and subsurface conditions, enable you to do that. But unfortunately, at this particular site, the site conditions and the subsurface conditions, and I'm going to describe the subsurface conditions further, but at this point, I will tell you that with the site conditions, as you can see in the foreground of the picture, having water, and the subsurface conditions being cohesion of soils, we had an issue with dewatering requirements, as we had challenges with temporary shoring systems. So we chose an indirect approach to make an assessment of the existing piles. And I want to share that with you in terms of what we did. The first prong, it was a three-prong approach. The first prong was the advancement of exploratory boreholes. And with the exploratory boreholes, we advanced a total of 6, as you can see here, the solid dots. And we had some previous boreholes as well. So from the 6 boreholes, we were able to determine the subsurface conditions. Now, we chose the selection or the locations of these boreholes very carefully, because I'm going to describe here shortly that we coupled the exploratory boreholes with some geophysical testing at some of the borehole locations, specifically 03, 05, 04, 05, and 06. Okay, and I'm going to share with you what I mean in terms of selecting the locations and how we actually advanced the boreholes. So some of the boreholes we drilled from the roadway surface, and we tried to get those locations as close to the abutment pile locations as we could, as illustrated on the slides on the left, where we advanced boreholes off the roadway. We use portable equipment as illustrated here on the photo on the right. Still trying to get as close as we can to the abutment to enable us to do the geophysical testing afterwards. But in terms of the subsurface conditions, because obviously there needs to be a determination of the subsurface conditions to assist in the capacity assessment of the pile that I get into a little bit later, but also to assist in the service life or durability part of the assessment. But very quickly, you could see on the slide here that the subsurface conditions that were determined were comprised of some fill, underlain by a thin layer of cohesive silty clay to clay silt, which was in turn underlain by a sand and gravel deposit, as you can see here. But the predominant deposit was a silty, sandy till of glacial origin. And you could see from the slide here that the piles in red are founded on that very competent silty sand till. Then we proceeded to the second prong of our testing, if you will, our investigation. And, what we did is we applied 4 different geophysical methods to enable us to determine the embedment length of the piles. Unfortunately, we didn't have any as-built drawings. We had design drawings, and we kind of knew that they were 8 meters in length, the piles, that is. But we needed to validate that. We needed to verify that. And consequently, we use 4 different geophysical methods: a parallel seismic method, a borehole magnetometer method, an electromagnetic method, and a natural gamma methods, right? So we use the boreholes that we advanced, and then use the different methods. The boreholes were advanced below the expected tip of the deep foundations. And the essence of all of these tests is to look at differences, variations, going from the bottom of the hole. We put in a 2-inch PVC, grouted the annular space, and then we started from the bottom of the hole using either a geophone, for example, with the parallel seismic method, or using a magnetometer for a borehole magnetometer, going from the bottom and then going in decrements up to kind of look at variations or changes with depth, so that we could ascertain the embedment lengths of the piles. That was the primary purpose of the geophysical testing. Here's some slides that just illustrate the testing in progress. So we got the seismic survey, the magnetometer survey, and the electromagnetic gamma survey, going from left to right. Here are the results. So we did engage our service provider who specialized in geophysical to help us out with this. And you could see from the plots here that we try to plot the results of the different geophysical methods. And, from this, you could see, for example, when you look at the red line, which are the results of the magnetometer, that there was a spike here at the top, as there was a spike here at the bottom, which is indicative of the cap at the top, and indicative of the fact that, from at this point here, that's where the pile tip was located, and consequently below it wasn't there, and you could see that change. When you look at the borehole below, and you look at the black line, and you look at the gradient, plotting, the distance versus time with the geophysical seismic method, we looked at the slope of the line, and from that slope, you could see here that the gradient of that line changes, and from that, we're able to conclude that this was the tip elevation. The other methods, unfortunately, didn't work so well. That is the natural gamma and the electromagnetic methods. And the conclusion that we made with that is that the batter piles influenced the ability to get the accurate results. That was the primary reason. And of course, when you have battered piles, it means now that the location of the borehole is more distant depending on the batter. So it was the spatial distance that influenced the inability to get accurate results with those two methods. The third prong was taking a number of samples and doing corrosivity testing. So there was a battery of testing that we did, including resistivity, chloride, and pH, and a few others. But for the purpose of the presentation here today, you could see from this particular slide that we plot resistivity with elevation, chloride with elevation, and pH. And we also superimpose based on criteria that we extracted from different sources to assess corrosivity, that the red is very corrosive, the green is less corrosive. And that was applied to all the different parameters. And you could see here that from the resistivity point of view, that it was the superficial soils that demonstrated not so favorable conditions. So above the water table. Below the water table, we're pretty good. Similarly with the chlorides. Above the water table, not so good. But below the water table, the conditions were much better. So, from that, we were able to, this is actually the sources of plotting those lines. Just for your information, that's how we came up with the identification of whether it was a corrosive environment or not for the different parameters. So from this, we made an observation and we made a conclusion in terms of whether these piles are in an extreme situation for corrosion moving forward, or whether or not we could live with it. And, looking at the different codes, Caltrans and NACE and your codes and the British standards, we were able to conclude that we felt comfortable enough based on further analysis to proceed. And I'm going to describe that further analysis. So with the corrosion assessment, we looked at Caltrans, we looked at a few other specifications and codes, and said, okay, here is the section loss that we could look at, right? Caltrans has this, other jurisdictions have a little bit less. So with the conditions that we had, we felt that going with the 0.015 millimeters per year, we felt comfortable with that, so that we could calculate what the corrosion loss was during the existing service life, and then predict what the further corrosion loss would be moving forward. So with that calculation of 0.015 millimeters per year per face, we came up with a conclusion that there was a 35% corrosion loss, or a total corrosion loss past and future would be 35%. So with that 35%, knowing, of course, the grade of steel and the strength of steel, we calculated 790 kilonewtons from the, a factored strength of the pile. And once we made that calculation based on a 35% loss, and looking at the demand, we concluded that we were good from a structural capacity perspective. And we did a similar assessment for the structural capacity. And with the structural capacity, we used empirical methods to compute the capacity, the actual capacity of the pile, knowing that the pile derived this capacity both from shaft and tip resistance. We came up with our factored capacities, and then compared it again with the demand, and concluded that we were okay also from a geotechnical capacity perspective. So we were good to go from a service life perspective, a durability perspective, a capacity perspective. and we've now proceeded accordingly to design the structure to replace the girders and to replace the deck. And in fact, there was a meeting scheduled today that I could not attend because I'm here sharing this information with you to kind of finalize, the contract package. So this is going to be tendered shortly. But I wanted to share this slide with you to give you an indication of the, the value of the investment. And I'll get to that in a second in terms of what the savings are. But the cost, as you can see from this particular pie graph, for the three-prong approach was, about $75,000 Canadian. Most of it was the exploratory boreholes, and then you had about 20,000 for the geophysical, and the corrosion testing was just over 3,000. So, conclusions. We concluded that obviously using an indirect methodology is acceptable to make an assessment of existing piles. We've concluded that it's cost effective, of course, to reuse existing piles. And having said that, I'll get to the second bullet first. On this job, we did our calculation in terms of the savings compared to reuse of existing foundations versus having to build new foundations and a whole new bridge, and we came up with $500,000 cost savings. The total investment was about 75, with some engineering and reporting, maybe 100, but the net savings came to about $400,000. But there's the other advantages, as I mentioned as well, in terms of reducing mobility impacts, traffic disruptions, environmental and sustainable advantages as well. So moving forward, it is our intention here at the Ministry of Transportation of Ontario to continue to ride the investment in testing in general, and certainly specifically when it comes to the reuse of existing foundations. We've got a couple of projects on the radar where we want to expand and not only consider doing the indirect testing, but we're looking at doing some direct testing where we could actually expose the piles, locate and expose the piles, subject the piles to axial compression testing, similar to what we heard from previous presentations, lateral load testing, extract the piles is something that we're planning to do, and do some actual testing of the whole extracted pile to assess corrosion loss and to make an evaluation of durability. Of course, this will all be combined with determining the subsurface conditions. So that is our plan moving forward. And that concludes my presentation.
Tony, thank you very much. Truly appreciate it.